For lecture 6, we are going to study Monte Carlo methods for optimization. So this will be two applications for Monte Carlo simulation. So after we know how to generate random numbers or random variables, we can then use them for simulating the so-called stochastic processes. That is, the process that involve randomness. In particular, we shall simulate two biological processes that involve randomness. One is the particle swarm method for optimization, and the other is the so-called genetic algorithm for optimization. So first, particle swarm. So you can think of this as a model for, say, a flock of birds, or a school of fish, or bees, or ants. So those are the animals that they work together, right, in a group. For example, let's think about a flock of birds. So those birds try to find food in a field. So each bird is considered as a particle, and those particles, they form a group. They interact with each other in search for food. So for that problem, let's use the notation X, and here I use arrow to denote this is a vector, consists of d elements, x1, x2 to xd. So this is just a d-dimensional coordinates of a point in this d-dimensional space. For example, d equals 2 in the bird case, where the bird try to scan over a two-dimensional field. So here for optimization, we often have a objective function, which is a function of the coordinate. For example, in the one-dimensional situation, we have such a function. So x star gave us the maximum, global maximum. So we may think of f in this case as a value function, and we want to find the most valuable place. And another example, we may also think of we want to minimize a function. In that case, f of x is interpreted as a loss function, and we want to minimize the loss function. Sometimes people also interpret this f as a cost function. So we want to minimize the cost, or a energy function. So we want to find the most stable place, the lowest energy place. Okay, so we can find the global minimum. So those functions may be multimodal, means that there can be multiple local minimum. And in the case of optimization, there can be multiple local maximum. And we want to find the global minimum or global maximum. So for two-dimensional situation, it will be a two-dimensional function so that the curve become a surface. But in general, in the d-dimensional situation, we will go over the d-dimensional coordinate. The function is a function defined on the d-dimensional coordinate. So you may wonder why this is a difficult problem. So in one dimensional, we just find a grid of points, and then we go through all the points on this grid, and we find the minimum, right? And in 2D, we can also divide the domain into a 2D grid, and we go through all the points on this grid. We find the minimum or the maximum. But this type of method quickly become infeasible because in the d-dimensional situation, suppose you divide each dimension into n grid points, and then together you have n to the power d grid points. In two-dimensional, you have n squared grid points, right? But in d-dimensional, you have n to the power d grid points. For example, if d equal to 100 and n is, say, 1,000, you have 1,000 to the power 100 grid points. There's no way for you to go through such a large number of grid points and evaluate each point by f and find the global minimum or global maximum. It is totally impossible. So therefore, you need more efficient search algorithm to find the global minimum or global maximum. In the search algorithm for such a f function, which may have a lot of local modes, local minimum or local maximum. So usually we use a method that combines exploration and exploitation. So exploration means that we just explore different places. And exploitation is that if we find a good place, we then search near this good place to exploit what we have already discovered. Okay, so that's the basic idea. It's a combination of exploration, it should be plus exploration and exploitation. So usually, if we don't have a good understanding of this objective function, then we may use some generic optimization methods, such as a particle swarm or genetic algorithm. In fact, in both of the algorithms, we do not even need to have the derivative. And X may also be defined in a very complex discrete space. Okay, so here the idea of exploration is very important, especially if we have multiple local minimum or local maximum, depending on whether we want to minimize the function or maximize the function. And then for exploration, often we need some randomness for exploration. And in fact, as we will see later, randomness is very important for integration. And it gets around of the so-called curse of dimensionality. And this also underlies its effectiveness for exploration. So let's go back to the particle swarm. And let's see how we combine exploration and exploitation. So suppose we have m particles and we number them as I from 1 to m. So those are the particles. And then just like m birds, so those m birds start to search. So we need two quantities for each particle. So this the first quantity is the position of the particle. So the coordinate for the particle at time t. So let xit be the position of the ith particle at time t. And for example, in the situation of a bird, then x is two-dimensional. So we look at the position for ith bird at time t. And we also need the velocity, which is a change of the position. So we use vi of t to denote the velocity of particle I at time t. Again, in the bird situation, v is a 2D change of the coordinate. So what we do is we first randomly initialize the positions and the velocities. For example, they follow some uniform distribution for each bird at time 0. So this t equal to 0 at this point. Okay, and then we start to update this position based on the velocity. So here xi, there should be I, xit plus 1 will be xi, this should be I, xit plus vit plus 1. So that is, this is a current, this is the previous position, this is the current velocity, and with this velocity, the bird moved to the new position, which is xi, here there should be I, xit plus 1 equal to x, this should be I, t plus vit plus 1. Okay, so here we use the discretized time. Otherwise, for continuous time, we should use delta t. But in discrete time, we just let delta t equals 1, so that this v is the change of the position per unit time. So we just add v directly. Otherwise, it should be v times delta t. And then the key here is actually how do we update this v? We know that in physics, the change of v is acceleration, and acceleration is decided by the force. So F equals ma, right? That's the Newton's law. And we have something similar. So the change of the velocity depends on some factors. And this is a key equation for the particle swarm modeling. So VIT plus 1 equal to W times VIT. So W is called in inertia. So this is a coefficient often less than 1. It's like a friction, right? So if it's less than 1, then usually you reduce the velocity. And but you want this to be close to 1. If it's close, very close to 1, that means you know, the surface can be very smooth. Or in the case of birds, the birds actually is in a cruise. state. So it keep its velocity without much change. Okay, but usually W is a number that's less than 1. But then there's some things that actually very much like a force. So we have C1 times R1, and then times P biased I minus the current position of I. So that is the P biased I is the particle i's, the ith particles, the best place so far up to time t. So for example, for the iceberg, and then the iceberg, remember the best place the bird has visited in terms of the food availability or the food abundance, or maybe the food quality. And let P bias I be the best place that bird I has visited up to time t or so far, okay? And then you see that here, this is a 2D position, this is 2D position, that's the current position. And if we add a C1, C1 is a constant or a parameter in this model. So this is called cognitive coefficient. That is whether this iceberg recognize or remember the best place it has visited. Okay, and R1 is a random number from like uniform from 0 to 1. So this stands for the randomness. So the bird make decision more or less randomly. And then you see that this term actually makes the V to be along the direction from the current position to the best place. So that is this term drag the velocity towards the best place visited by the iceberg so far. Okay, and then we have another term which is G best. This is a group or global best. That is the best place visited by all the birds so far in terms of food availability, abundance, or quality. Okay, so this is, but this is all measured by F. So this is so you for each bird you measure the maximum. Suppose we want to maximize F. So the maximum for F for the positions that the bird has visited, and this is the maximum among all the best positions among all the birds. So this is a global best. There shouldn't be I. So this global best is just the best among all the I from 1 to M, among all the M birds. There's a typo, there shouldn't be any I here. So this is a global best. And then this term also force the bird to go towards the global best. So this C2 is another coefficient, a constant, which is the social coefficient. And R2 is another random variable uniform from 0 to 1. And R2 is independent of R1. So here you see that we have R1 and R2. So those are the randomness. They give us exploration. So we don't have a deterministic dynamics. So we have randomness in R1 and R2. This allows us to explore different change for velocity. So they give us exploration. But then the personal best, P best, personal best, or the particles best. So each bird's best place. So this we want to use it for the purpose for exploitation. And this is global best. There's now I global best. We want to use it for again for the purpose of exploitation. And this is C1 means this cognitive coefficient means that the bird memorizes the best place it has visited so far. And the C2 is social coefficient. So the bird also knows the best places visited by all the birds so far. Again, the best place means that you want to find this position among all the positions visited by all the birds. You want to find that position with the highest F value if you want to maximize this F. And similarly, for this one, this means among all the positions visited by the icebergs, you want to find F. You want to find the position with the highest F value. Okay, so the most valuable place, the best place. So therefore, you see that when you change the velocity, so it is almost like dragged. So this is like a attractor. So this attractor drag the velocity toward this place, and this is also a attractor drag the velocity toward this place. So that is the bird want to stay on the course, on the current trajectory, but also the birds want to go back to its personal best and go back to the global best. So this global best is computed among all the positions visited by all the birds so far, evaluated by F. So we look at which position has the best or maximum F value among all the positions visited by all the birds so far. So this is how we find this G best. Again, there's no I, but this P best I is I's bird's best place. Okay, so this two terms for exploitation and R1 and R2 give us exploration. So we are not always go directly go to the personal best. So we also have some randomness. Sometimes this R may be close to 0. So that means we just stay on course. But sometimes this R may be close to 1. That means we really want to go back to the past. So sometimes you are in the exploration mode, you just try to do things. And sometimes you maybe have some target, right? So that is you want to somehow go back to the best place you have visited so far. So that's the basic idea. And so those are the explanations for those terms. So P best I is the bird bird's best location, and G best is the best among all the birds. So the G best is computed as if you have a controller, right? Central controller to compute the best among all the birds. But actually the birds does not have the leader. There's no central controller to compute G best. So this model is not entirely realistic. So that is the social part of this model is not very realistic. Maybe the social part is still like a bird may also follow its neighbors, right? So that is each bird want to go back to its personal best, and then the bird may also want to follow its neighbor's behavior. So there's some attraction or some repulsive force. So that may be a better, more realistic model. But for the purpose of optimization, this may be good enough. Okay. And then we just keep running this system, simulating this system with the randomness here. And then we can simulate the dynamics for the whole flock of birds. And eventually, those birds will hopefully converge to the global maximum if we want to maximize this F function. And again, this can be very useful in the high-dimensional situation, even though we got our inspiration from this two-dimensional like exploration for the bird. Okay, but our goal is actually to use it for high-dimensional optimization problem, because there's no way we can search over a high-dimensional grid. There's so many points in this high-dimensional grids. Okay, so another algorithm is a genetic algorithm where we want to maximize f of x. Here again, this f is an objective function, and we can interpret this f of x as a fitness function. And for genetic algorithm, the first thing we need to do is to represent this x as a genetic representation. That is, we want to represent x as a binary string. So x may be within a discrete space, and we still need to find a way to represent a discrete configuration as a binary string. But x may also be a continuous value. In that case, we just use a binary expansion for this continuous value. So this binary string or binary sequence is very much like a DNA sequence. Although in the DNA sequence, we have 4 letters, A, G, T, C, but in the binary string, we only have 2 letters, 0 and 1. But this actually, there's not much loss of generality, because in computer, we just work with the binary sequences. Okay, so that's the first step. We find the genetic representation of this X. And then the next step is that we want to then to use this F, the fitness function, to do the selection. So we first initialize the population as a random binary strings, and then we use f of x to select the members, the members of the current population to be the parents, so that they can breed for the next generation. And this is done by the crossover and the mutation to generate the new generation. So the crossover is like this. So suppose we have two strings. For simplicity, I let one string to be all 0, one string to be all 1. So you can see clearly. And then crossover means that we randomly select a position and then we swap. So that is after the crossover at this random position. So the first string become 1, 1, 1, 0, 0, 0, and the second string become 0, 0, 1, 1, 1. So we just swap the two pieces at this position. So this is a crossover, and for each sequence, we can then do the mutation. So for example, for the top sequence, here, let's focus on the top sequence. We can do the mutation so that we, at each, for each like letter, we have a probability, say 5% probability to flip it. So suppose this, we flip this letter and this 0 become 1. And we flip this one, this 0 become 1. So we get a mutated sequence. So we just do this independently for each position. And we flip with a certain probability. Okay, and we can do the flip mutation similarly for the second sequence. So this enables us to generate next generation. And then we continue to go back to do the selection and then crossover and the mutation. And eventually, we will find a population for binary strings that give us very high F values. So that's the idea for genetic algorithm. So both the particle swamp and the genetic algorithm are very simple, and they draw inspiration from the biological process, just like a neural network, also inspired by the biological brain. So, and this can be used for optimization, especially if you don't have much understanding of the objective function or the underlying problem. So you just use this generic algorithms to do the optimization. Especially they are very simple, and they do not even require computing the gradient, and they can work for discrete and the continuous situation. So very simple methods. Okay, and here you can see that when we do the crossover, we need to randomly find the position. And when we do the mutation, we also need to do the random, we mutate with certain probability. For example, if you want to simulate a probability for 5%, you can divide the interval from 0 to 1 into one short interval from 0 to 0.05. Right? And then from 0.05 to 1. And then you randomly generate U. If U belong to the first interval from 0 to 0.05, you then flip it. Otherwise, you just keep it. So this enables you to mutate each position with 5% of the probability. Okay, so now you can see that random number generation can be very useful for generating such random process, which enable us to do the optimization. And again, here you can see that the selection is enable us to do the exploitation, right? So we only select the fitted members, just like in the animal kingdom, those males, they fight, right? They fight each other. So there's a selection process. And then the crossover and the mutation enable us to do the exploration because of randomness. So we can then explore the solution space. So that's a very powerful method. Again, a combination of exploitation in selection and exploration in crossover and mutation. Okay, so now I think we are ready to study the second part, the Monte Carlo integration. In fact, the reason that randomness works in Monte Carlo integration also underlies why random exploration works in Monte Carlo optimization. Okay, so let's think about this Monte Carlo integration. So suppose that we want to calculate the expectation for a random variable. So the expectation for a random variable x follow f of x can be visualized or can be considered as the population average for a population of n points, where this n is considered to be huge, almost infinite. So for example, let's look at the hat. the height of all the people in the US population for 300 million. And suppose we measure the height in infinite precision, so that those are the different numbers, and we just label them as x1, x2 to x capital N. Capital N is 300 million. And then we can draw a scatter plot for those points, so that each point is a person based on the height of this person. And it's dense here, less dense here. So the density is like this one. So a density can be used to describe a population. And when you randomly sample a point, then let x be the point that you sampled, the x is said to be sampled from this density. Okay, so x follow f of x. But intuitively, you can just imagine x as a random point among these capital N points. And these capital N points are described by this density function. And then we can think of expectation of x as a population average, which means you sum over all xi for I from 1 to capital N, and you divide this by capital N. So this is the population average, and this is the expectation of the random variable x, which is a random point sampled, selected from this capital N points. Okay, and this is a sample average. And one way to compute this average based on the density is that you can divide the range into those small bins. So each bin is x plus delta x, so equally spaced small bins. And then instead of summing over all the xi for 300 million xi, you can consider sum over the bins, so that all the points in each bin take the same value x up to a imprecision caused by this infinitesimal delta x. So that is, we assume the height of all people in this bin equal to x. So there's some imprecision, but as delta x go to 0, then it doesn't matter. And this n of x is a number of points in this bin, or number of people in this bin. Okay, and then we have this so many people in this bin, and each of them has a value x. So therefore, their summation in this bin will be x times n of x. Okay, so this is how we compute the sum, and we sum over all the bins, and we divide this by n. So this will be the summation for over all those bins, x, and then we move this n inside. So nx divided by n. So that will be the proportion for the points within this bin. Okay, and this, according to the density, is the density times delta x, or in other words, the proportion divided by delta x become our density. So therefore, the proportion is f of x times delta x. Okay, so this is summation over all the bins, x, fx, delta x. So as delta x go to 0, then this converge to the integral. So integral is really just a sum over a large number of bins. So x, fx, so delta x, this infinitesimal delta x become dx in this integral notation, and this is elongate s, stands for summation. So therefore, we can more formally define E of x if x follow this density f of x to be the integral x fx dx. Remember that here is what we want to sum over, and this is the proportion, which is fx delta x. Okay, so by the same logic, then you can also define the expectation of h of x. For example, x is the height of a random person, and h of x may be the square of the height. Suppose we are interested in some population average of the square for people's heights. Okay, and then we can, by the same logic, we can define this as integral of this is h of x, what we want to sum over, and the fx dx. Fx dx is still the same as E of x as the original definition. So we only need to replace x by h of x if we want to compute the expectation of h of x. Okay, so that's the general definition. And as to notation, usually we use mu to denote E of x, population average. And then we can also define the variance of x as the expectation of a special function. This function is x minus mu squared. So that is, we look at the difference between x minus mu and we square it so that we don't care about whether x is bigger than mu or smaller than mu, whether it is above average or below average. We square it so that we only care about the squared deviation. And this is the definition of the variance. And we often use the notation sigma square to denote the variance. We add the square because this is on the squared unit. Okay, and because E is population average, so therefore this variance is actually the population variance, which is the average of each xi. So we go I from 1 to, this should be capital N, I from 1 to capital N, which is 300 million. And then for each xi, we look at the difference from population average and we square it. So that is variance is actually the population average of squared deviations. And similarly, by the same logic, we can define variance of h of x, any transformation of x, as the expectation of hx minus the population average of h of x and then squared. Okay, so that is whatever quantity you want to compute the variance. So always this quantity minus expectation of the same quantity, and then you square outside of the difference, and then you average over the whole population. So E is average over the whole population. Okay, so that's the variance of h of x. But here, this is a key definition, and everything else just can be considered as a special case. And Monte Carlo integration means that we want to compute a integral I, which is the expectation of h of x, where x follow f of x. So by definition, this expectation is the integral of h of x, fx dx. For example, so h of x may be square root of absolute value of x, and f of x may be this density function of normal distribution. So in order to compute that, remember this population average, and we can approximate this by the sample average. That is, we sample small n heights or small n values from this f of x. From this is our f of x. We already know how to generate normal random variables, right? So it is as if we have like a population of 300 million people, and this is described by the density, and we draw 1,000 people. This n may be 1,000. And we measure their heights or whatever x value. So it is, then we say that x1, x2, and so on, and xn are generated from this f of x independently. Okay, and then this is a population average. We then approximate the population average by the sample average, which is average of this small n for h of xi. Okay, so for each x, we compute h of xi, and then we compute the Monte Carlo approximation, which is the sample average. So this we use this to estimate our integral I, and we call this I hat. So we put a hat on top of it, meaning that this is an estimate of this I based on the random sample from this population. So because xi are random, so this one is also random, meaning that suppose each one of you doing the same experiment, and each one of you will report a different number. So this I hat is a random number. So hopefully this number will fluctuate around the true quantity I that we want to approximate. Okay, so here again, the paradigm is that we have a population for endpoints, which can be described by a density, and this n is almost infinite. And then we randomly sample a small endpoints. Say this big n may be 300 million, and this small n may be 10,000. And then this is a random sample. Suppose we want to estimate the population average. Given the density, then this population average can be expressed or can be idealized as an integral, which means we want to approximate this integral. And then we can approximate this by sample average, this sample average. Okay, we use sample average as estimate of population average. Because this is random sample, so the sample average is random. It fluctuates around the population average, and the magnitude of the fluctuation can be measured by the variance of this I hat. Okay, so hopefully the expectation of I hat equal to I, meaning that I hat fluctuate around I. but the variance of I hat hopefully is very small. And in fact, we will show that the variance of I hat is inverse proportional to n. So the bigger the n is, the smaller the variance is. And a special case for this h function is indicator function. And if we average over the indicator function, binary indicator function, we then get the proportion. So this is an important fact that we should be aware. So that is h of x equals 1 if x is within a certain set A, certain range A, and it is 0 otherwise. So we can either use notation indicator 1a of x or simply 1 of x in A to denote this function. And then if we look at the population average of this function, so that is 1 over capital N, summation I from 1 to, again, here, this should be capital N, a typo, capital N, and then the indicator function of xi in A. So this will be the population proportion for all the points in A. Okay, so that is, because here you are just count how many points are in A, and then you divide this by the total number. So you get the population proportion. And if you randomly sample a point, then the probability you get a point in A will be the population proportion according to axiom 0. So that is under random sampling, the population proportion become the probability that a random point belong to A. So this is from axiom 0 under equal likely sampling. And so therefore, you see that this is a population average. So it is actually the expectation of this indicator function. And the expectation for a binary function then become a probability for this A, okay, which is the integral of f of x within this range of A. So that's the basic idea. And a special case. So therefore, you see that when h is a binary function, then the population average become population proportion. And we can then, and the sample average become sample proportion, so that we can use sample proportion to approximate population proportion. And under random sampling, we know that the population proportion is the probability, right? The probability for each random point belong to this region. And then this probability can be estimated by the sample proportion, which is also the sample frequency. So we can use frequency to approximate the probability. Although, as we said before, the frequency being an average of indicator function is random. It fluctuates around the true probability. Okay. So now let's look at one example. So we want to compute this integral, which is square root of absolute value x, and then this is a normal density dx. So this is our f of x, this is our h of x, right? So we want to compute, this is the expectation of h of x, or the population average of h of xi. Small xi. So this small xi goes from the whole population. And then what we do is we generate x1 to xn, say this n may be 10,000 from this density, which means we just randomly sample n points from this large population of capital N points intuitively. And then we approximate the population average, which is I here. This is expectation, which can be interpreted as population average by the sample average. So the sample average will be 1 over this small n. This small n may be 10,000, and then sum over I from 1 to small n, and then square root for this hxi, which is square root for xi. Okay, so this is the sample average. We use this sample average to approximate this integral. So this is a Monte Carlo integration. Okay, another example. So let's look at, suppose we want to approximate pi. And so we have the unit square. This is our sample space. And so consists of all the points in this unit square. Now let's look at this curve, x squared plus y squared equals 1. So the area below this curve, let's call this region A. So this area is pi over 4, right? And then if we randomly sample point, or if we randomly throw a point into omega, the probability that this point fall into A, according to axiom 0, because of the equal likely sighting, will be the size of A divided by the size of omega. And here the size is area. The area of A is pi over 4, and the area of omega is 1. So the probability is pi over 4, because this is a quarter of a circle, a disk. And we define the disk, the area of the unit disk of radius 1 to be pi. So this is how we define pi. But we don't know how to compute pi. We know how to define pi to be the area of the unit disk, but we don't know how to calculate pi. And then Monte Carlo method come into the rescue. So that is, we can just randomly throw n points, n may be 10,000, randomly throw 10,000 points into omega, and then we count how many points fall into A. Suppose m points fall into A. If n is fixed at 10,000, this m is actually random. Okay, but intuitively, the frequency that the point fall into A, that is m divided by n, should fluctuate around this probability, which is pi over 4, right? So that is the number of points m in A divided by the total number of points should be roughly proportional to this area of A divided by the total area, which is pi over 4. So therefore, with this Monte Carlo experiment, we can then estimate the pi by 4 times m divided by n. And again, this pi hat is random because suppose each of you do such experiment, throwing 10,000 points into this unit square, then each of you may have different m, so that each of you may have different estimate of pi. So pi hat will fluctuate around the true value of pi. So that's the basic idea. And later we shall study the expectation of pi hat. Hopefully it is centered around pi, but fluctuate around pi with a certain fluctuation. And the magnitude of the fluctuation again can be described, characterized by the variance for this random variable. Okay, so this is a Monte Carlo method, and you can think of this probability of A as the expectation of this indicator function that x squared plus y squared is less than equal to 1. So x and y is a random point in the unit square. So x is x coordinate, y is y coordinate, and then x squared plus y squared less than equal to 1 means that xy is below this curve, or xy belong to this A. Okay, so therefore, this is an expectation, and this expectation can be written as an integral, right? Integral of this function, and this is also an integral for within this A, right? Integral within this A, which is area of A. Okay, again here xy is a random point from this unit square, so that each x and y follow uniform 0 to 1 independently, so that x, y together form the coordinates for a random point in the unit square. A real-life example, maybe which we may consider to be the earliest example of a Monte Carlo integration, Monte Carlo calculation, is a Buffon needle. So that is, we want to approximate pi in real life instead of using computer. At that time, there's no computer. So we drop the needle of length L onto a paper ruled by those horizontal lines, where the distance between two adjacent lines is d. Okay, and we just keep throwing a needle, and the size of the needle, the length of the needle is less than d, and then we count how often the needle crosses the line. So this frequency actually is a function pi. So if we can calculate this frequency, or it's approximates the probability, and the probability of crossing is a function pi, so that we can find a approximation of pi. So that's a basic idea. And to calculate this this probability, so we can think this way. So let's look at the center of each needle, and so the center can be anywhere, right? Anywhere. And if we just look at the two adjacent lines, it can be anywhere, the center. But it is symmetric around the center line, right? So we only need to assume that the center is a uniform from 0 to d over 2. Because if it's for this range, we can fold it back to this range. So we only need to consider this range because here is symmetric by the folding. And the other places are also symmetric by the translation. We can translate what happened here to here, right? So we only need to consider this part. And here is the center. And let this be 0, and this is y. And this part is L over 2. And this length here, I made a mistake. That's my fault. So this height is L over 2 times sine theta. So theta is angle. So this height is L over 2 times sine theta. So the point is that if our y, this center, okay, the center of y is less than L over 2, then this point will touch the horizontal line. So that is, if you think about here, so this is a horizontal line. And if this is the angle, and this is the theta, and this height, this is my fault. So this height here is L over 2 sine theta. So now if your y is above, if the center of the needle is above this L over 2 sine theta, then you see the needle, this needle will not touch this line, right? If it's below, the needle will be here and it will cross this horizontal line. Okay, so that's the idea. So that is why the center of needle follow uniform from 0 to d over 2, and theta is the angle which is uniform from 0 to pi. And the needle will touch the horizontal line if we have this condition. So that is if this is happening, I need to go to the next page. Please let me go to the next page. Okay, yes. So if this y, the center, the coordinate, the height of the center is less than or equal to L over 2 sine theta, if that's the case. Okay, so therefore we only need to compute the probability that y is less than or equal to L over 2 sine theta, where this theta is uniform from 0 to pi, and y is uniform from 0 to d over 2, and y and theta are independent. So therefore, y and theta is uniform within this rectangle. And the region where only when y is less than L over 2 sine theta, so that the needle touch the horizontal line. So that is, we want to know what's the probability that a random point in this rectangle fall into A. So that would be the area of A divided by the area of omega according to axiom 0 in the equal likely setting. And the area of A will be the integral, right? The integral of this curve. So L over 2 sine theta d theta, where theta go from 0 to pi. And that will be L over 2. And the indefinite integral of sine theta is negative cosine theta. And then you have 0 to pi, and then divided by d over 2 times pi, which is the area of the rectangle. And then this integral, if you look at the difference, this is 2, because cosine 0 is 1, cosine pi is negative 1, right? So this is 2. And then you have L divided by t over 2 over pi. So that is the probability of crossing is 2L over d pi. So this is a probability. This probability can be approximated by the frequency. That is how often, if you generate 10,000 points, which means you throw the needle 10,000 times, then what's the proportion or frequency of the points fall into A? So that will be very close to this number. So if you can, you get this frequency, you can solve for pi, right? Pi will be equal to 2L over D times this frequency. And the frequency can be obtained by repeatedly throw the needle onto the paper and see how often it crosses the line. And then you can estimate this pi. So this is maybe you can consider this the first Monte Carlo method in real life. I think we can stop here. So next time we shall study Monte Carlo integration in detail.